Cool. All right. Hi, everyone. Thank you so much for coming out here tonight. My name's Cassidy Westjohn. I'm the Public Programs Coordinator here at the List Visual Arts Center. This is a series, welcome to, let me say this again, welcome. This is the Graduate Student Talk with Megan Masterson. It's a series where we invite graduate students to expand on our exhibitions using their expertise in a similar subject matter as a way to see how art and research are overlapping on MIT's campus. Tonight we'll be hearing from Megan, a physics PhD candidate at the MIT Kavli Institute for Astrophysics and Space Research, where she works on some of the most extreme objects in the universe, supermassive black holes. Megan's work focuses on understanding how these black holes grow. She uses both ground and space-based telescopes spanning multiple different wavelengths of light to map how material accretes onto these cosmic beasts. Megan is involved in many astronomy outreach initiatives, including Astrobites, Astronomy on Tap, and MIT Astrogazers, through which she shares her passion for science communication and the wonders of the cosmos. In this talk, Megan will connect many of the themes that permeate Pedro Gómez-Egaña, The Great Learning, including temporality, intensity, alignment, to the mysteries of the cosmos. She'll specifically discuss how these themes persist in her own research on the growth of supermassive black holes, where the intense gravity distorts our view and influences our perception. At the end, you'll have a chance to ask a few questions. And until then, thank you. I'll give the talk over to you. Thank you.
Hi, everyone. Thank you all for coming. I'm really excited to be here today to explore the connection between art and astronomy. Thank you, Cassidy, for that nice introduction and the invitation to give this talk. Can everyone hear me before I get started? Okay, great. If you can't at any point, just let me know. Okay. So before I get started, I want to say one final thank you to Pedro Gómez-Egaña, the artist whose work you're seeing around me today. We had the chance to meet earlier in February when he was here setting up the exhibit, and it was a really informative discussion that we got to have together. There's a lot of different aspects of this exhibit, and I can't talk about all of them today, so I encourage you to go and explore, in particular, Virgo in the other room. So today I'm going to be talking about specifically this piece, The Great Learning, and its connection to supermassive black holes. So I spend most of my days thinking about black holes, the most extreme objects in the universe. These are something that are so heavy, so dense, that not even light can escape their gravitational pull. So I think we all learned pretty early on in our childhood that there's something that's keeping us here on Earth. That's the force of gravity. When you jump up, gravity pulls you back down. But the Earth's gravity isn't actually that strong. We, human beings, can launch rockets that travel fast enough to be able to escape the Earth's gravitational pull. But for black holes, there's no such rocket that could ever escape their gravitational pull. Not even light, which sets a sort of cosmic speed limit, is able to escape them. Now, out there in the cosmos, there are two main kinds of kinds of black holes that we see out there. I gave you a spoiler. One of them is called a stellar mass black hole. These are about 10 times the mass of our own sun, and they're the end state of massive stars. So when massive stars run out of fuel, they will collapse and die in a violent explosion called a supernova, and they leave behind these stellar mass black holes at their centers. Now, our own sun is not going to explode in a violent supernova, and we'll talk later on in this talk about what the end state of our own sun is going to be. Now, on the other hand, on the more extreme end, the more massive side of things, we have our supermassive black holes. And these are 1 million to 1 billion times the mass of our own sun, and they live at the center of nearly every galaxy, including the Milky Way. Now, despite the fact that we know that they exist in nearly every galaxy, we actually don't understand how supermassive black holes are formed. And this is a very active area of research to understand their formation and also their growth. So we've talked about how black holes, nothing can escape them. So then how do we actually study them? How do we know that these stellar mass and supermassive black holes exist out in the universe? Well, the primary way that we do this is that we study their effect on their surroundings. So in the Milky Way galaxy, we looked at the center of the galaxy, and we actually traced the motion of individual stars over time, and these traced out an orbit around a relatively empty region of space relatively quickly. And so using the same sort of physics that governs the motion of planets in our solar system, astronomers were able to back out that there's a 4 million solar mass black hole sitting at the center of our own galaxy. And this was a discovery that was awarded the 2020 Nobel Prize in Physics. Now, in other galaxies, we can't actually trace the motion of individual stars, and so we have to turn to other means with which to study the supermassive black holes and infer that they are there. One of the ways that we do this is by studying supermassive black holes that are surrounded by a lot of gas. And what they'll do is they'll gobble up this gas through a process known as black hole accretion. Now, black holes in popular science are often thought of as akin to a vacuum cleaner. And this really isn't the case. It's actually hard for these black holes to gobble up this gas. If you think about the planets in motion around the sun, they kind of stay at a fixed orbit. This is thanks to a property known as angular momentum. And in order for this gas to actually be able to fall into the supermassive black hole, it needs to lose both angular momentum and energy. We have a friend acting up here. We have to actually lose angular momentum and energy from this gas. And the way that the gas does this is by heating up and emitting light. And this is light that we can see with our telescopes here on Earth and in space. So today we're going to be talking about one particular supermassive black hole. And I'm going to take you on a story of discovery and try to relate it to what's going on here in the great learning behind me. The galaxy in question, or the supermassive black hole in question, is named 1ES 1927 plus 654. It's at the center of a galaxy, and it's at the center of my heart. It's a source that I've been working on since the start of my PhD, but it was actually discovered in the 1970s with an X-ray telescope named after Albert Einstein. Now, X-rays are a particularly powerful way of studying the accretion of gas onto supermassive black holes, and that's because this gas gets really hot and produces this high-energy X-ray emission that we can see. So one of the reasons why we're talking about 1ES 1927 plus 654 today is because it's kind of this cosmic oddball. It's really, truly like no other black hole we've ever seen before. But in order to give you a kind of glimpse into what normal black holes look like, in order to give you a glimpse of why 1ES 1927 plus 654 is weird, we need to talk about what normal black holes look like. And in particular, like I mentioned, we can't trace the orbits of individual stars around supermassive black holes. We also have a very hard time taking a picture because these supermassive black holes and their surrounding gas are really quite small on the sky. And so we have to turn to other techniques to actually measure what's going on physically. And one of the techniques that we use is to study the amount of light that comes to our telescope as a function of time. And this helps us kind of map out how this accretion process actually works. And so around most black holes, when they're accreting gas, the process is relatively random and stochastic. And so if you were to transform, for example, light into sound, it would sound more like noise. Like if you listen to white noise when you go to sleep, that's kind of what it would sound like. Or if you put 100 musicians in a room and ask them all to play a different song, it wouldn't sound like a kind of beautiful melody. It would sound just like noise. And that's where 1ES 1927 plus 654 became quite different. In 2022, what we saw with our telescopes in terms of light sounded more like a melody. And Cassidy's going to play that melody for you now on this piece called Deep Rivers. So hopefully you can hear the kind of repetitive rise and fall from this piece, and that's essentially what our X-ray telescopes saw. They saw the amount of light rising and falling repetitively every 18 minutes or so. And this is kind of unheard of around supermassive black holes. We only have a handful of them that have actually shown these sorts of oscillations. So what gives rise to this sort of periodic behavior that we're seeing? Well, one nice thing that gives rise naturally throughout the universe to periodic behavior are orbits. Just like we all know that Earth is orbiting around the sun with a period of a year, right? This is something that imparts itself on our daily life all the time through the seasons. So what if we put something in orbit around our supermassive black hole? Well, this 18-minute period means that this object has to be extremely close to the supermassive black hole. And I think this is exciting in and of itself that we found potentially something orbiting around the supermassive black hole. However, the story kind of gets a little bit crazier. Actually, it gets a lot crazier. 6 months after this initial observation, when we went back and looked with the same telescope, and what we saw was that the oscillations were still there, but they were now happening every 7 minutes instead of every 18 minutes. And so our period had been cut by more than half, and this was kind of unheard of around supermassive black holes. And to think about it in terms of this orbiting companion analogy, we can again turn to our solar system, right? So Earth orbits the sun with a period of a year. Now Mercury, which is much closer to the sun, orbits with a much faster period. So this is kind of generally how orbits work. So if we're going to shrink our orbit from an 18-minute period to a 7-minute period, we need to bring our object closer to the supermassive black hole. And this 7-minute period is kind of pushing the limits for what we can do. We're really starting to get extremely close to the black hole's event horizon, which sets the kind of point of no return beyond which we can't see any light. So in some ways, this is kind of akin to what's happening in the Great Learning behind me. The force of gravity is tugging the Great Learning down to Earth. In our supermassive black hole, it's very similar, but it's actually the emission of gravitational waves. These are ripples in space-time that carry away energy and shrink our orbit from our 18-minute period to our 7-minute period. So with gravitational waves, we can actually go and predict when our object should plunge into the supermassive black hole. And once it does that, once it's inside the event horizon, there should be no more oscillations that we see. So we turned to our calculators in our general relativity textbooks, and we calculated that in January 2024, our object should plunge into the supermassive black hole. Then we observed the system in March of 2024, 2 months after this prediction, and we saw that the oscillations were still there. Not only were they still there, they were still there at the same 7-minute period that we had seen before. So is our companion model wrong? Or could there be something else that's giving our companion an additional kick that's keeping it out of the black hole and allowing it to kind of teeter on the black hole's event horizon? Well, this is where I think our analogy to the Great Learning grows a lot stronger. So in the Great Learning, there's not just the force of gravity that's dragging this bar down to Earth, otherwise it would be on the floor now. There's actually these strings that are giving it this force of tension that's keeping the Great Learning up in the air. And Pedro Gómez-Egaña has kind of engineered these counterweights over to the right here that are kind of almost perfectly balancing the force of gravity. And this balance leads the Great Learning to kind of just stay hanging here, but the gravity is winning ever so slightly as it's falling to the ground here. So what if there's some additional force that's keeping our companion out of the supermassive black hole? Well, one possibility is we know that when objects, our companion, can transfer a little bit of their material onto another, they can actually get an additional kick. And so what we need is a companion that's actually giving the supermassive black hole some of its own matter to be able to receive a little bit of kick back outward to stay out of the supermassive black hole. That's kind of what's being depicted here in this image that we had made up about this supermassive black hole. But what sort of object can do this? It turns out that not any object can be put in a 7-minute orbit around a supermassive black hole. If you put a smaller stellar mass black hole in orbit around the supermassive black hole, there's no way for it to actually transfer some of its matter, and it's driven purely by the emission of gravitational waves. What will happen is you will rapidly get that stellar mass black hole to plunge into the event horizon, and there's no way to get around this. On the other hand, if we put our own sun in a 7-minute orbit around a supermassive black hole, it would be torn to shreds. There's no way for a star, an ordinary star, to kind of survive in this extreme gravitational environment. However, luckily, there are things that live in between stars and black holes. In particular, there are these objects known as white dwarfs that have a kind of special type of property that we'll talk about that actually puts them in the sweet spot to be our companion for these observations. So white dwarfs are the end state of stars like our own sun. So I mentioned earlier that the sun is not going to explode in a violent supernova. When the sun runs out of fuel, it's actually going to slowly shed its outer layers, and it's going to leave behind this compact core of material, and that's what we call the white dwarf. Now, this white dwarf is compact and quite dense. It packs about a sun's worth of mass into about the size of the Earth, and this extreme density is really what helps us in this environment. So It's the fact that it's so dense means that it's not going to be shredded apart like our own sun would be, but its density is nearly perfect so that it can start transferring material onto this supermassive black hole to get that additional kick that fights against the gravitational wave emission. So one of the things that I want to highlight about this discovery and this potential model for what's producing these really strange oscillations is that this is not something we came to in isolation. This was really a collaborative process, and it took collaborating with people who work on systems other than supermassive black holes to see that a white dwarf in orbit around a supermassive black hole could actually work. So most astronomers who think about white dwarfs mass transferring, a number of them actually think about double white dwarf systems, where you have two white dwarfs in orbit around one another. And these sorts of systems are found scattered throughout our galaxy. And detailed observations have revealed that, yes, both the emission of gravitational waves and this additional kick from the process of mass transfer are at play in these systems. And so it was through collaborating with people who work on these sorts of systems that we realized that we could potentially use the same sort of physics to explain our observations here. So what does this model predict? And what does this tell us about the supermassive black hole? Well, it's the first object that we know that's actually potentially teetering on the edge of a supermassive black hole. It's kind of pushing the limits in terms of how close things can survive. And in particular, it makes a key prediction that we can test with the next set of gravitational wave observatories. The spiraling of this white dwarf around the supermassive black hole should produce these ripples in space-time. And there's detectors that are out there set up that are going to be detecting these sorts of gravitational waves. Now, the detectors here on Earth that have already detected gravitational waves are a little too small to detect the ones that we would see from this system. But luckily, in the 2030s, we expect a telescope to launch into space that will be large enough to capture the gravitational waves from this system. So we've made a prediction that we should be seeing gravitational waves if this white dwarf is in orbit around the supermassive black hole. OK, so I think I've finished with my story, and I just want to tell you a little bit about kind of the connections that I see to the great learning and Pedro Gómez-Egaña's work. So there's some literal metaphors that I've drawn upon here to explain our observations. But I think I also want to draw upon the kind of more figurative connections here. In his opening night, Pedro described the great learning as super simple and super complicated. And I think this is something that really resonates with me when I think about 1ES 1927 plus 654 and this story that I told you today. Which is that we're using physics that by themselves are not that complicated. They're relatively simple, but we're piecing them all together to try to explain this kind of complex behavior. The other thing about the great learning is that every time you put it up, it responds differently. I was here a couple of months ago, and it never moved as quickly as I saw it move today. And I think that stochasticity, that randomness, is really exciting, and it's really a lot like how we do astronomy. We make predictions for things, and then we go out and we observe them, and they're totally different. And that's part of, I think, just highlights to me why we do astronomy and this kind of innate human curiosity that we have and that we're using to learn about the universe. It's very similar to, I think, a lot of the themes in this work. And lastly, both the great learning and Virgo, one of Pedro's other pieces in the other room, where you kind of see this distorted home view, have taught me that patience and diversifying your perspectives are vital to doing your science. I told you about how collaboration with people who work on topics that are seemingly unrelated to you was important to making this discovery. And similarly, I think in astronomy, we have more literal things like working at other wavelengths. But in total, I think we need not a single viewpoint and not a single snapshot to be able to understand the cosmos. And I think the same is true and holds in life and in this exhibit. So thank you.